All right, let's pray. God, we thank you for this time. I pray that you would help me to wake up and Lord, just bless this math lesson in Jesus' name. Amen. All right, so today we're talking about matrix algebra. So here's the idea. All this stuff that we've been doing with matrices is actually useful in real life. Whoa. Totally cool, man. Okay, here's why. So let's say, I don't know, that I'm programming, I can't be a missile. What can we program?
A computer.
A computer. To run a missile, no, to run an aeroplane. Okay, and the airplane is flying, right? But I want it to turn a little bit. So usually the direction of an airplane is given in 3 coordinates: the x, the y, and the z. Right, where x is like that way, and y is that way, and z is forward. Okay? And so let's say that my velocity in x, y, and z is like, well, I'm going forward, so let's say 500 miles per hour, and then I'm kind of turned a little bit to the right, maybe. I'm not going up at all. So I'm just kind of cruising that way. Well, there are matrices that you can use to multiply this and get it to go and change direction. It's pretty cool. It's called a rotation matrix. And it will rotate this vector a little bit and then give you a new vector that's rotated by however much you tell it to rotate. So we multiply matrices to get new matrices that will be similar. So let's say we take this, and then I want to rotate it just a little bit. So let's say that's our rotation. Yeah, that's fine. So when I multiply this, I take this row times this column, and so I get 1 times 5, which is, thank you, one person. 1 times 5, which is
5.
Plus 2 times 0.
0.
0.
You're writing in pen.
Hmm?
I just messed you up, huh?
I cheated.
Okay, 1 times 5 is 5. 2 times 0 is 0. 0 times 500 is 0. So I retain my 5. Then I have 1 times, or 0 times 5, which is 1 times 0, which is 2 times 500, which is, whoa. So man, this means that thing is turning like way up, right? And then 0, 0, 500. So we multiply matrices to use them to describe motion most often, okay? This also can be used to solve systems of equations. So it doesn't have to be a motion equation, it could be some other equation. You don't have to know that. That's just like, because you're always like, what is this real and real? What is this useful in real life? And it's like if there's anything in pre-calculus that you actually use in real life, it's probably that. So today what we're going to do is we are going to find the inverse matrix. And the inverse matrix is a very, very special matrix because we can use it to solve a system of equations. So we've learned Cramer's rule, which is one way it's kind of painful to solve a system of equations. An inverse matrix can be used to solve as well. Unfortunately, I'm taking my time. I don't know if they actually want you to learn the real way or the fake way.
There's always a fake one.
Yeah, they're going to teach you the fake way. Okay, so
What's better?
you're not there yet. You'll get there. You'll get there in the next 5 lessons. It's fine. So if you have a matrix A, B, C, and D, there is a matrix that you can multiply this by in order to get rid of this entire matrix. And when I say get rid of, I mean you multiply by some matrix and you get the identity matrix, which is this one. Okay. Why do we like the identity matrix? Because if you multiply it by anything, it gives you itself. So just like in addition, we call the identity property of addition when you add 0, you get itself. Or like if you add 0 to 5, you get 5. In multiplication, if you multiply anything by 1, then you get itself out, right? This, for matrices, is the identity. If I multiply anything by this, I will get the same thing I started with. So if I multiply I get 2.
Wait, so if you divide those two then, what?
Matrix division doesn't exist. Good question. Okay, so we like the identity matrix, and we want to find this matrix, which is called the inverse matrix. It's special because if you multiply something by the inverse matrix, you get the identity matrix. This will be important in a moment. So, how do we find the inverse matrix?
Multiply by that.
Simple way? You take 1 over the determinant of the original, and then you flip some things. So that is the inverse matrix for my God!
No,
Thank
I'm
you.
just confused. I'm so lost. What? Wait, why did you just turn them different?
Because that's how you get the identity
Is
matrix.
that like you?
For a 2 by 2. Yep.
Okay, cool.
So, we'll learn the actual way to find it later. So let's try and find the inverse matrix for 1, 2, 3, 4. So you're going to do 1 over AD minus BC, so AD, it's basically the determinant of this, times, so you switch these two, so it'll be 4 and 1, and then these two become negative.
And then what do you do?
Multiply this. So 4 minus 6 is -2. So my inverse matrix is -2, 1, 3 halves, -1 half.
Wait, what did you do?
I multiplied this into these. Because this is -1 half, so then you distribute.
Oh, okay.
Shall we check and see if it works? If it doesn't work, this whole thing's not good. All of computers die, basically.
Oh no.
So I said that this times this should equal that. Now, important point. It has to go after your matrix. If it goes before, it may not work. It might actually. I'll take that. Okay, So let's multiply. How do we do matrix multiplication? You take the row times the column. So 1 times negative 2 is? 2 times 3 halves is?
-3, or just 3.
3. Negative 2 plus 3 is? 1. Now we're going to take this row times this column. 1 times 1 is? Minus? Now we take second row, first column, which is going to live in the second row, first column. 3 times negative 2 is? 4 times 3 halves is? Second row, second column. 3 times 1 is? 3 minus 2 is 1.
Whoa.
So that's how you find the identity or the inverse matrix. Now, why is this useful? How will this apply in our real life? What are the biblical applications of this? I mean, I think it's cool that God just set all this in motion. I can tell you how to solve an equation with it. And you guys can use that in your futures for biblical application. Oh, I was never that teacher. I'm always a long stroke eraser. I was never like that. It's because I'm tired. I didn't. So, watch this. This represents that set of systems of equations. 1, 2, 3, 4 can be written like this. Let's put some random numbers here. So what we're really doing is we're representing a system of 2 equations in 2 variables in matrix form. So if I take this matrix times xy, I get this left part. If you don't believe me, take your row times column. 1 times x plus 2 times y. 3 times x plus 4 times y. So that's this half. I'm saying that equals 0, 2. Now here's where it gets a little funky. Oh, you can multiply on either side. That's cool. Okay, so here's what I'm going to do. I'm going to multiply by my inverse matrix on the left side of each part of this. You ready for funky? Here's funky. I'm going to multiply it in here. Got it.
I'm awake. I'm in shock right now.
Okay. Here's what happens. On this side, I've already shown that multiplying these 2 together gets you the identity matrix. The identity matrix times anything is just that something. So this whole left side is now just xy. So whatever this equals, x will equal the top thing, and y will equal the bottom thing. So now all I have to do is multiply these two matrices. What's negative 2, 1 times 0, 2?
0.
Because that represents negative 2 times 0 plus 1 times 2. This one is the second row times this column. 3 halves times 0 is 0. Negative 1 half times 2 is negative 1. So x equals 2, y equals negative 1.
Whoa. Wait, so if you do, but doesn't that always equal 1, 0, 0, 1, the one on the left? So if you solve it like that on that side and then multiply it by that inverse function, does that work with everything?
Each matrix has its own inverse matrix.
That's what I'm saying. Like if you can solve that, that's so cool.
No yawning. Not sympathetically yawning.
Sorry.
Okay, don't receive your yawn. I'm rejecting your yawn. I'm moving on. I'm moving
I don't
yawn.
receive it.
Okay, let's try another one. And then I'm on to you guys. How do you do the eyebrow thing? I don't get it.
It's so simple.
What's up?
Ooh,
For sure. Okay, we're gonna solve this. Okay, first step. Fine. We're all yawning. This is not good.
Are you yawning?
She yawned because I yawned. Okay, so you're going to find the inverse matrix. Then you're going to multiply it on the left side. You can't multiply on the right side of this because it won't work. So it has to be on the left. So, how do we find the inverse matrix? It's 1 over the determinant. So that's going to be 5 times 10 minus 6 times 8. And then you're going to switch these numbers and make those negative. So 15 minus 48 is 2. So I'm going to multiply this times 1/2. Then I'm going to multiply my equation, which is 5, 8, 6, and 10 times xy. Is it confusing where I got these numbers from? These ones?
Yeah.
Okay. So I pulled each of the coefficients from the x, each of the coefficients from the y. And if I multiply them times the matrix xy, then I get what I started with, 5x plus 8y. And then I get 6x plus 10y equals whatever these things are on the right side.
Do you add or subtract?
This is multiplying.
Yeah.
So when you're doing matrix multiplication, it's always adding. Don't yeah me.
Sorry.
Yeah.
Sorry.
Yeah.
I was like,
My mind is going a mile an hour.
Okay, so then I multiply on the left of these by my inverse matrix. Okay, these will cancel because it's the inverse times the original. So you get the identity. So if you multiply this out, you get your answer. How do you multiply this out? 5 times negative, so it's the row times the column. So this row times this column. 5 times negative 4, which is negative 20. Negative 4 times negative 6, which is 24. So that equals 2. If I do this row times this column, so negative 3 times negative 4 is 12. 5 halves times negative 6 is minus 15. So that is negative 3. So what that's saying is x is 4. Y